And we are going to host this technical event in collaboration with our department and I'm confident that this event will provide valuable insight about the application of electronic IC design. Once again, I extend a warm welcome to all of you for participating in this event, and I extend my best wishes to everyone for a productive thinking exchange. Thank you very much. Now, I would like to invite our guest to address the session.
Thank you very much, sir. It's a pleasure to be here and appreciate your invitation for this lecture or this particular presentation from my side. A very good morning to all of you. Uh, I hope it's all well over there. Let's have it as a nice interactive session. It's not going to be heavy. It's going to be a very light session. It's just to introduce you to the various industrial concepts or something which is trending in the industry currently. So if you have any questions, feel free to interrupt me. But in case you don't have the facility to interrupt me so easily, you can always shoot me a mail, or through your professors, you can get in touch with me. Okay, let me start sharing my presentation. Let's go ahead with that. Um, do you see my screen? Okay, wonderful. So I hope for the next 90 minutes we'll have a good time. So what is this presentation all about? It is just going to be a very high level presentation about artificial intelligence. What is machine learning? I think you already have a course on artificial intelligence. I don't think this will make much of a sense. Then something on probably edge computing. Then we'll get into the core of it, the semiconductors, which is enabling all these things in this world, right? So the idea is to put them all together and let's all discuss about it and see how we can get to use these things in future, as well as be aware of what are the things which are the trends which are happening in the industry right now. So I have a couple of videos. So I hope you all enjoy the videos also. So let me just start with artificial intelligence. Artificial intelligence is a very broad area, right? But it is very important to understand what this artificial intelligence is, what is machine learning. There is something called deep learning. Let's try to just little bit connect the dots. So I would like to start with what is machine learning. Oh, I know that students there, we all learned in our universities and colleges. Um, there is a lot of stuff we get from our professors, our teachers, right? There is a learning there. There is something which we are trying to understand, comprehend, put our logic into place, right? So, how can a machine learn? That's a very interesting concept. It's something which needs a very deep thought, in my opinion. It's a field of study that gives computers the capability to learn without being explicitly programmed. Being programmed is something very different. It's just lines of code being executed, and it could be an iterative process. Sometimes you know about the brute force algorithms. You try to do all the combinations and see which one fits it. That one is not really. It's more of programming or putting into sequence some certain steps, right? But that's not what we really want. We want the machines to think. You would have heard about machines taking their own decisions. I hope most of you watch movies. You would have seen a lot of movies and where the machines take over, or they are able to do a lot more things, right? They are able to predict things, understand, comprehend, make a decision. Um, that's real artificial intelligence. Let's see how we are able to do this and what is really enabling that. So, machine learning I would say, is a subset of artificial intelligence. Artificial intelligence is a broad category. Machine learning comes within it. So, in simple words, we can say that artificial intelligence is a technology that will enable computers and machines to simulate human intelligence. Because we are supposed to be intelligent, right? That's what is making us very different from animals. And the other most important thing which we need to know is its problem-solving capability. So, humans, we are able to invent things. That's the difference. We are not trying to just learn from our teachers. There is a lot of research going on in universities and different places, right? Even in industry or universities or even in defense or whatever it is. Why we are able to do that? We are trying to find new solutions which has not been existing anywhere else. That is intelligence. That is the smartness we have. So if that smartness which human brain has, if that can be extended even to some part to machines, that is something really wonderful. That's what this artificial intelligence is about. I just want to just touch about the person by name, author Samuel. He's the person, he used the term machine learning for the first time. So, but let us start with a small video, maybe for 10 minutes, and then we'll have more videos to follow, and then we'll have some lecture going on. Let me. Just before I continue, I just want to know whether you are able to see my video shot. Are you able to hear the audio? Can anyone confirm, please? Okay, okay. Video is also visible, right? Good.
In the early days of computers, one would frequently hear them called thinking machines or electronic brains. Now, of course, they weren't actually brains, and they couldn't really think. It was a natural error, though. After all, these new machines could perform calculations in just a few seconds that would take a human months or even years to complete. And yet, as amazing, not to say massive, as these machines were, there were all classes of problems that resisted machine solutions. Early attempts at voice synthesis were largely successful, but voice recognition remained a stubbornly hard problem. Early computer graphics were crude but could produce usable pictures, but image recognition algorithms provided mostly disappointing results, and computers could be programmed to ace simple games like tic-tac-toe, but more complex games like chess firmly resisted algorithmic solution. A common belief was that as computers inevitably became more powerful, that these problems would become solvable as well, and for a while, that belief seemed to be confirmed. One by one, many of the problems that seemed to be intractable fell to the unrelenting power of Moore's law. For example, the game of chess was seen as something that would remain dominated by human players. Now, there are free chess apps one can download for smartphones that can tackle all but the best human players. Yet, for all of the advances in computing power over the decades, even today, there remain classes of problems for which there appear to be no easy algorithmic solutions. These problems frequently center on classification, determining the subject of a photograph, for example, or extracting keywords from a spoken utterance. For a human, this is easy. We look at a photograph and say, oh, that's Uncle Bob at Jimmy's birthday party. Even listening to me speak right now, your brain is interpreting the audio signal, sorting the sound of my voice from other sounds in your environment, and turning these sounds into cogent ideas. Why is it so frustratingly hard to make a computer do that? Let's go back to the chess problem for just a moment. A beginning chess player, knowing only the rules of the game, will look at a particular arrangement of the board and try to figure out all possible moves, then choose a move that seems to provide the best advantage, or at least minimize the damage that may come in subsequent moves. An experienced chess player, though, will look at the entire board and recognize patterns. They'll see that they control the center of the board, or that they've limited their opponent's lines of attack. Or they might even think, hey, I've seen this board before, Boris Spassky, 1970. But it took a long time before programmers figured out that for any board arrangement, you could enumerate a list of possible moves, then weight them for player advantage, take each of the new board arrangements and enumerate every possible move for them, and weight them for player advantage. And at each stage, the least advantageous board positions are eliminated. After some number of move levels are evaluated, the most advantageous move is selected. Here's the point. The experienced chess player treats the board as a classification problem. What arrangement best matches advantageous positions I've seen before? But the computer treats the board as the input to an algorithm to be iterated to some desired depth of moves. Computers are, at their core, just very fast devices for running the steps of an algorithm. For example, to sort a list of numbers, a computer might search for the smallest number, then exchange the first number in the list with that number, and then restart the search with the second number in the list for the next smallest number, and so on. As long as the problem is reducible to an algorithm, a computer can be programmed to handle the problem. Chess, like the sorting problem, is ultimately reducible to a set of steps that can be executed by a computer program. A brain, on the other hand, is a collection of units called neurons. A neuron typically has many inputs, but a single output that may go to multiple other neurons. When certain input conditions are met, the neuron fires, sending either an excitatory or an inhibitory pulse to the neurons to which it is connected. Arranged in layers and with the weights of the excitatory or inhibitory pulses properly scaled, a neural network can recognize features in its input set much more efficiently than can an algorithmic computer. The brain of a chess master, trained by years of studying and playing thousands of games, instantly sees whether a particular board position is advantageous or not. Well, in the world that doesn't involve board games, there is a class of problems that is well suited to the algorithmic model, and another class of problems that is much better suited to the neural model. No single model works best for all problems, and
Okay, we take a pause for this video. I think this was the content which I wanted to show off you. So the idea here was to explain that, okay, there is a couple of models which are there, and how we are going to correlate this model, the layers. For example, the person there was explaining that there is going to be this neuron firing multiple other neurons and going through stages. There are something called neural networks. They work in a very similar approach. This is at the high level which I want to just mention. Let me just get back to the presentation.
the best solution
Excuse me, just okay. Oh, sorry, I went back. So let's take a small break. Let's try to keep it a little light. I just want the professors are not your professors are not supposed to participate in this particular small puzzle. Can anybody guess what is this? What you see the picture, the image you see in your screen? Anybody who can make a guess what it is? Okay, clue number two. Oh, sorry. Somebody, sorry? Yeah. What is a typewriter? Not exactly. I'm not able to hear well, but if you are guessing it as a typewriter, not exactly. Let me go for the second clue. Somebody wants to take an attempt before that? There is a name for this machine. It's not a. Uh, I think I'm not able to hear it. So let me just go for the second clue for the benefit of their time. Okay, this is the second clue. I'll go for the third clue also. Somebody who can guess the person. Okay. Uh, okay, let's settle. I will talk about this. Um, this person is by name Alan Turing. The mission you see on the right is called the Turing mission. What it is, we'll talk about it a little later. And the mission you find to your left is called Enigma. There is a movie called The Imitation Game. Okay. If you guys like hearing stories, I can tell you a small story. Alan Turing, he's actually the first person to come out with computational complexities, talking about the computer. He was actually, you can say, the first person to lay the framework for computers. And in those days, when the World War was happening, um, one side was the German, its allies, and the British Empire and their allies, right? So there was a direct war happening between Britain and Germany. So there used to be a lot of technologies which are being developed because the war is the time when the most of the new inventions happen. So this Enigma mission is what was being used by Germans to send signals or coded data in those days. It's an encryption mission, right? It had a lot of billions of combinations by which you can encrypt your data and send it across. So it is always good to have the information ahead of time by the enemies or by the other party so that they will take appropriate actions, right? So this person, of course, along with other some other scientists also, he came out with a mission which could decipher this. Okay, if you have an opportunity, watch this movie called The Imitation Game. It's very interesting. This particular invention, they say that it reduced the wartime by 2 years. They defeated Germany because of this particular mission. Not exactly this mission. This mission was the one which has been used by the Germans. He developed a mission which could decipher that code. It's a very interesting move. That's called the imitation game. Okay. What I want to focus here is this person by name Alan Turing. You would have heard about computational complexities, right? Why am I bringing computational complexities here? Because it's all related to the computations when you're talking about artificial intelligence, when you're talking about deep learning and so on. The fundamental thing when you're in a college, I think the focus should be on research, right? You need to understand what exactly you're doing, how you can extend that problem further, work on it, right? So whenever you are developing an algorithm or coming out with a solution to a problem, you try to tell in terms of complexities. I'm not sure whether you learned about something called polynomial time problem, um non-polynomial time problems, and NP hard, NP complete. These are categories of problems. Let me just give a very high level this thing. Polynomial time problems are every problem when they are telling in terms of computational complexity. Um, you know that assume that your system is the black box, which is going to take the problem and work on it. So there are some inputs which you give. For example, you give four inputs, then they try to tell the complexity of that algorithm in terms of the number of inputs. Polynomial time could be like the number of inputs to the power x or something. For example, number of inputs are n to n square. That could be the amount of complexity for the problem. Suppose if it is an exponential problem, it takes huge amount of time. 2 power n or something is very, very hard because you have a lot of combinations. It may even take years for humans to solve most of the problems. So polynomial time problems are those problems which you can solve in polynomial time, which means that you don't have to wait for a very long time. For a reasonable computer, you can do it with enough computing resource and so on. So here also there is something like one which you a decision problem. A decision problem. Okay, let me just put two perspective. A problem is I can one thing is that to get a solution, you try to do a lot of things. You try to do a lot of processing. Another thing is that you have a solution, you just plug it in and see whether it works or not. For example, you use your mobile phone, right? You just try to give the code or you try to give a pattern, right? And your mobile unlocks. So these are problems where when you give a solution, okay, it can immediately check and tell whether it's correct or not. If it is correct, it will unlock the phone in front of you and give it. If it is not correct, then you don't really uh, you're not able to solve that, right? You don't really go and see whether okay, that's what the hackers do, right? They want to hack your phone. That means they need to solve for that solution and get it right. For example, another example the Sudoku problem, right? Sudoku problem, if you have the solution, you can just plug. I hope you guys have played Sudoku. You just try to plug in the numbers and see whether it's correct. It's easier. But to solve a Sudoku problem, it may take a lot of effort and time, right? I'm just trying to give some perspective examples. Some problems are easy to solve and easy to check whether that solution, one of the solution fits in. That is both are possible. But some problems it is not easy to solve. But if you have a solution, you can plug in and check whether it's okay or not. That is the second category of the problem. The first category is called polynomial time problem. The second category is called non-polynomial time problem, or it's called non-deterministic problems. There are also other categories of problems, which may not be, I think, through a lecture like this, it may not be very easy to explain. But what I'm trying to say is here is that these are the computational complexities and different kind of problems. So let's step a little bit more into this artificial intelligence and let's try to see how much we know about the world, what is happening. Many of you might have used uh, Google Maps nowadays. At least in Bangalore, we try to use Google Maps a lot of it because we get stuck in traffic a lot of time. So we want to find the route where the traffic has been, take the alternate routes and so on. Uh, Google Maps or some of the systems may not be using GPS of the position of the car or anything or the data of the GPS, but uses something else. You know what? How does it and tell that okay, traffic in this route is very high, in this route is very less? Any guesses? Anybody wants to attempt? Actually, there is a lot of echo in the room. I'm not able to understand what's being told. Okay, maybe I think you have already got the answer, I suppose.
Number phones will be counted at the area. They will use the
Yes.
data of the track. Google must use the data.
Correct, correct. They just use your mobile phone transmission signals, right? How many mobile phones are active in that area? Because everybody has a mobile phone in this days, right? So if the number of people are there with mobile phones, obviously there is more number of people on the road, right? That's one way to calculate one data which has been used. And you might have seen, right? You're going and doing a Google search, and suddenly you are searching for a mobile phone. Next, they will give recommendations, advertisements, everything. You go to a YouTube video or anywhere, you will see the recommendations for mobile phone. Or if you're planning to travel to some place, it will tell about the travel websites, different places, the airlines, blah 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 blah, all these things. How are they able to get all these data? That means whatever data you are searching and everything is being analyzed. That means a huge amount of data which you're feeding in your search engine or whatever is being used and it's being analyzed. You're not aware of it, but it's being used. Be careful with your data, with your social networking things. Okay, your data is being taken, it's being used. Some people use it for good information, but goes to the wrong hands. It could be in the used for anything which could not be really, which could turn out to be bad for you, right? So be always be careful. Okay, these things come with the responsibility, right? Everything has a good and bad. Science itself is like that, right? Technology, I would say, technology itself is like that. Some technologies can be good to good use, can be put to bad use. So it is up to us to decide how we want to do it. Just let's be very responsible and let's make sure that the data privacy and other things are taken good care of. I think you guys all know about it. Let me just get back to the slide. And I just want to jump in and give a very high level understanding, and we'll have a video for you all to enjoy and get a better understanding about AI or generative AI as we are going to talk about it. So AI, as I said, it has several things, right? One is called the machine learning, and other one is called the neural. Okay, we can say directly go to something called the deep learning. Okay, and for anything, you need a model to be created. An algorithm is needed. Okay, these AI algorithms, after all, you're going to, there are people, experts in that who are going to model it. How good that AI algorithm is. For example, ChatGPT is good. Gemini is it's not all that great. Okay, something is good, something is not good. Why these differences are coming? Okay, these differences come in because there is a way they have been modeled, there is a way the data is being collected, and the way the data is being processed. Today, we have very huge compute. We have big data centers and cloud data storage as well as processing power is so high, we're able to take huge amount of data, process it. But how efficiently it's processed, that depends on the model, the AI model which has been used. Okay, and based on that, so somebody who's able to model it well and who can use that model to get the right data or right information from the all that data and use it for the decision making or problem solving, that's more important. So they can learn from the available data, and they can make some classifications based on the data. There is also something called structured, unstructured. Machine learning is more structured. That means it needs human intervention to classify the data and tell that, okay, these are these categories, understand this, and the machine starts learning. Now we have gone to a level where um, uh, the machine itself can classify the data. Okay, it's more complex. It involves much more complexity, of course. Okay, and it starts predicting things, right? It starts predicting it. These are the things possible. Not only gives the possibility, but which one is more favorable. All those kind of things are possible. We don't want to play a zero-sum game, right? We just want to make sure that we are winning it, or at least we have a higher probability of winning it. So these the algorithms are based on such type of thoughts and decision-making process, which means that the modeling has been done in that fashion. So, as I said, deep learning is a subset of machine learning. And I was telling about the multi-layered neural network or something like that, right? What you said. So it's more convoluted in the sense that, okay, from one stage to another stage, it has multiple layers. Even one layer can do a lot of things, but you have more refinements going down the layers, more computation, more data which has been processed, and more precise things. You have a limited set of data, and you have a limited processing of it, then it's going to be your output is going to be limited in terms of accuracy, right? You have more stages, that means it's becoming more and more smarter and intelligent. So it can go for, this can go and simulate even complex decision making power. Um, but never think that, okay, something can supersede the brain. The brain is something which is very unique. But the good thing about these compute, this data, this big, this three things, particularly your model, your data, how much the computational resource and everything, how fast you can compute, how fast you can transmit data. All these things play a factor, right? Because you want things to be done. Humans cannot really process a lot of data in a short time, but it can do every other thing. It has a memory which is going to be so you can even remember something incident which has happened when you're 2 year old. Maybe you don't remember it, but suddenly you may get a flash of it. Maybe you remember something which you might have done maybe when you're 5 years or 6 years. How is that? What is that level of memory? So many years of data are being stored. Your vision is capturing it. It's going to the brain. The brain is processing it. It's storing it. How is it storing? Maybe everything is not like you go and retrieve it at some point, but some point of time, it may come to you. You may realize certain things at some point of time, right? I'm not going into superstitious things, but even naturally, it happens to most of us, right? So what is DNN? DNN, they call it deep neural network, or it's a neural network with more than three or more layers. The more the layers, it's better for it to identify, classify, recognize. And most of this, I want to say, is used for pattern recognition. When I say pattern recognition, it is used in many places. For example, uh, you have a particular part which is going into an aerospace or something. You want to analyze that, okay, this particular part is still good or not good. Maybe externally you see that and first recognize, no, this part is not good. We need to analyze it further. And very interesting in medical science, for example, somebody, is this a particular tumor or not tumor? You want to analyze it, right? So you can get that data, and now your artificial intelligence based tool would have analyzed so much of the tumors, in what shapes it can be, in what all forms it can be. That data has been already written, and now using all those patterns and making a decision on that, it will be able to identify, oh, this looks like a small tumor which is starting to come. Okay, maybe now alert this person or alert the doctor. This is possible. So there is a lot of pattern matches, data matches, a lot of things which are happening. Okay, so there is something very interesting from the IBM. There are many companies which work on artificial intelligence. Um, you would have heard about NVIDIA, right? NVIDIA, they make graphical processors and very complex, which are used for doing a lot of machine learning and other processing, which is related to artificial intelligence. If you see the stock prices in 2023, in 6 months period, it went more than 350 times. From $150, it reached around $450. Everybody is bullish about these particular artificial intelligence stocks because this is going to be the future. For sure, it's going to be uh, the future of everything in the everything. When I say that tomorrow, be it industry, be it academics, research, everything, your day-to-day life, you'll be using artificial intelligence in some form or the other. Even today, uh, yesterday we were using Microsoft Office tools and everything. Now they have added some artificial intelligence tool to that, right? You might have heard about Copilot and something like that, which will help you in, for example, Excel sheet. It helps you in telling, okay, you don't have to know how exactly to, you tell it and it will tell you the procedure, how you have to do certain things in Excel and so on. So things are becoming smaller, smarter, faster. So uh, we cannot leave this bus. We have to be there. But where we want to be, but we cannot really get into everything. Where we want to be, what is our field of interest, how you can contribute to that, that is what we need to think about it. And research is something which is the most important. I would always stress on it. Let's go for another video. I found this to be very interesting. I hope you enjoy
Arthur
it.
C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. And perhaps the first time that you played with generative AI, it did evoke a sense of magic. Suddenly, for the first time in our history, we have technology that can speak our languages, understand our requests, and produce entirely novel output. AI can write poetry and draw otherworldly images. It can write code. It can surprise and delight us with an original joke or musical composition. It can create, and an act of creation often inspires wonder. But AI is not magic. It's math and science. And it wasn't sudden. These experiences have been decades in the making. AI is going to touch every aspect of our lives. It will change the world. But how it will change the world is up to us, to all of us. Welcome to the AI Academy. My name is Dario Gil. I'm an electrical engineer and computer scientist by trade and the head of IBM Research, but also a business leader and a senior vice president at IBM. In this series, we are going to demystify AI. We'll show you how we got here, how generative AI works, and explore some of the ways that it will transform business and society. So let's start at the beginning. People have been speculating about the possibility that machines would someday think since the late 1800s. But the idea really took root with Alan Turing's seminal paper in 1950. Historians call Turing the father of AI. He theorized that we could create computers that could play chess, that they would surpass human players, that we could make them proficient in natural language. He theorized that machines would eventually think. Thanks to my career in IBM Research, I have seen and been part of achieving many of the milestones that Turing identified on the way to a thinking machine, including chess with Deep Blue, Jeopardy, and debating systems. But Turing was just the beginning. If Turing's 1950 paper was the spark, just 6 years later, we had the Big Bang, the Dartmouth workshop. A couple of young academics got together with a couple of senior scientists from Bell Labs and IBM and proposed an extended summer workshop with just a small handful of top people in adjacent fields to intensively consider artificial intelligence. That is how the phrase artificial intelligence was coined, and it marks the point at which AI was established as a field of research. They laid out in extensive detail many of the challenges that we've been working all these years to solve, and developed machines that could potentially think. Neural networks, self-directed learning, creativity, and more. All still relevant today. For perspective, this was 1956, the same year the invention of the transistor won the Nobel Prize. Now, we can have over 100 billion transistors on a GPU and banks of interconnected GPUs to provide the compute power to create and execute generative AI functions. All these years, the AI theories, techniques, and ideas have been developed in parallel with progress in hardware that resulted in dramatic reductions in compute and storage costs, all converging now to make generative AI real and practical. But I want to make this critical point. It's not just about powerful hardware and clever algorithms. The third, and maybe the most important ingredient, particularly when it comes to your business, is data. You can't talk about generative AI without talking about data. It's the third leg of the AI stool. Model architecture plus compute plus data. You hear about large language models, or LLMs, that are powering generative AI. So what are they? At a basic level, they're a new way of representing language in a high-dimensional space with a large number of parameters. A representation you create by training of massive quantities of text. From that perspective, much of the history of computing has been about coming up with new ways to represent data and extract value from it. We put data in tables, rows of employees or customers, and columns of attributes in a database. This is great for things like transaction processing or writing checks for payments to individuals. Then, we started representing data with graphs. We start to see relationships between data points. This person or this business or this place is connected to these other people or businesses and places. Data represented this way starts to reveal patterns. And we can map a social network or spot anomalous purchases for credit card fraud detection. Now, with large language models, we are talking lots of data and representing it in neural networks that simulate an abstract version of brain cells. Layers and layers of connections with tens of billions or hundreds of billions, even trillions of parameters. And suddenly, you can start to do some fascinating things. You can discover patterns that are so detailed that you can predict relationships with a lot of confidence. You can predict that this word is most likely connected to this next word. These two words are most likely followed by a specific third word, building up, reassessing, and predicting again and again until something new is written. Something new is created or generated. That's what generative AI is, the ability to look at data and discover relationships and predict the likelihood of sequences with enough confidence to create or generate something that didn't exist before. Text, images, sounds, whatever data can be represented in the model. We could do a limited version of this before with deep learning, which was an AI milestone in its own right. With deep learning, we started representing a massive amount of data using very large neural networks with many layers. But until recently, a lot of the training happened using annotated data. This is data that humans would label manually. We call this supervised learning. And it's expensive and time-consuming. So only large institutions were doing that work, and it was done for specific tasks. But around 2017, we saw a new approach, powered by an architecture called transformers, to do a form of learning called self-supervised learning. In this approach, a model is trained on a large amount of unlabeled data by masking certain sections of the text, words, sentences, etc., and asking the model to fill in those masked words. This amazing process, when done at scale, results in a powerful representation that we call a large language model. Instead of narrow use cases and areas of expertise, you could start to have something broader. Basically, these LLMs could be trained on huge volumes of internet data and acquire a human-like set of natural language capabilities. Self-supervision at scale, combined with massive data and compute, give us representations that are generalizable and adaptable. These are called foundation models, large-scale neural networks that are trained using self-supervision and then adapted to a wide range of downstream tasks. This means that you can take a large pre-trained model, ideally trained with trustworthy industry-specific data, and add your institutional knowledge to tune the model to excel at your specific use cases. You end up with something that is tailored for you, but also quite efficient and much faster to deploy. The current thinking is usually that you can apply this to language, but that sparks a question. What is a language?
Okay, I hope you like that video. Was it boring or useful? Can you hear me? Let me just check. Can you hear me? Okay, if you can just give a thumbs up, it's fine. I think it's good. Yeah. So you're able to hear me, right? Okay. Okay, let me just go ahead. So let's go to something called edge computing. Now that we have a little bit of understanding about artificial intelligence, what is machine learning and deep neural networks, um, I just want to introduce this term called edge computing. Uh, what is this all about? So I think you have courses on Internet of Things, IoT, and so on, right? Which means that lot of things have been done at source. Now you would have heard about Amazon Cloud. Everybody has a cloud platform where there is a huge amount of data which is being processed. So that is the data centers or the cloud centers. Okay, they are distributed all over the world, and that's going to be the central network, because with so much of speed and network, we are able to get the data in a very short time. But there is something called edge computing which has come into picture lately, and it has become very popular. You don't want to process all your information and take it to cloud. Can you do something very close to the source? That is where the data is getting generated. For example, if there is a medical system, you are trying to analyze certain things, should you really send all the data to cloud? No, maybe not. Maybe I can just try to remove unnecessary data. Maybe that's one processing I want to do at my near my source. Then only, and if needed, I can just try to connect it to or process some information which could be easily done, and probably keep only the rest of the information which needs complex processing to be sent to cloud. So this edge processing adds a lot of value because everything is done closer to the source, which means that it's faster, it's more efficient, less data transmission, and this is a trend which is also happening. So why am I bringing this into picture? Because when you're working with data, the data directly does not go to the cloud where you have the big machines. Even your own computers or your university, you have a lot of computers, right? They may be not being used. Maybe you can do a lot of processing with those itself. You do not really go to a third-party cloud and do all the processing. I just wanted to give an idea. For a small process, edge computing is good enough. Okay. Now, anyway, I think this is what I was explaining. Now let's go to the main part of it, uh, that semiconductors part of it. So you would have heard from our government also. There is a lot of incentives being given for the semiconductor industry. Micron is setting up its test facility, and Tata is working with a Taiwanese company, technology partner PowerChip, for setting up a fab. Then there are other companies also, Tower Jazz, and you would have heard about Foxconn was trying with Vedanta, and lot of interest in this particular area, and the government is also so interested. This is one area where uh, in our country we are not having enough technology information, or we don't have uh, enough capability to manufacture our own chip, particularly in the advanced technology. We are able to do something. Uh, in Chandigarh, we have the SCL and all, where they are able to make some um, older technology loan chips, but that's not good enough, because all the technologies, all the current trends. For example, you take your processor in your mobile or even in your TV, they are 5 nanometer or 2 nanometer. We cannot have something at 180 or 200 for digital process because it's slow, it's power hungry. We cannot really use those kind of things. So we need to get the technology, and we are lagging so much. We cannot really develop the technology from root. Right? We need to get the technology from some other country, some other company, establish it here. And even US is very, it's putting sanctions on China, not sharing the semiconductor technology. Why is this all happening? Because this is going to be the heart or brain, whatever you call it. It's going to be the source for all the things which is going to happen in the world. Artificial intelligence, edge computing, or cloud, data analytics, something has to process it. Something has to take all this data, process it, and give the data back, which means that the semiconductors, the transistors within them are going to be the key. So that is the reason why I call them the hardware neurons. What you see here is like the left side is silicon wafer, where you have the small reticles or the small squares, which you see are individual chips. They could be a chip which is a processor, or it could be a simple buffer, whatever it is. It could be an analog to digital converter, whatever it is. So, or it could be an SoC. Okay. So these chips are being packaged. That's what you see it. Inside the package, you have the silicon, which is sitting there. Now, this particular package is put along with the other chips on the inductors, resistors, and other things. The connections are made, and they finally go into your device, your mobile or your TV or your rocket or whatever it is. So this is the manufacturing process, which I just wanted to give a very high level idea about it. About So it has a different process. I'm not going to talk much about it. But what is so important or what is so interesting about it? This needs uh, uh, an environment which is dust free. You need very pure water, okay, and much more than that, you cannot have any power fluctuations or uh, which means that you need an environment which is very contained in a particular the tolerance levels are very less, which means that when you're manufacturing, even if there is even a small dust, if it goes and deposits in your silicon, it can create a short. It doesn't work. It will not work. So what do you do? So you cannot have many silicons not working in your wafer, which means that you are making a loss. That is the reason why in India we have a lot of power fluctuations. We don't have a very clean environment, or there is a pollution levels and salt levels which are higher, and it's very difficult to get all these things together. But you need to get an ecosystem where we can manufacture all these things. Then only we become self-sufficient in all the industries. Today we are importing all these chips. We are not manufacturing. 99.9% are getting imported. Even though we say make in India mission, the silicon is not being done. That the testing is not even done there. Only the maximum what is being done here is the design work. The design work, then again, it's sent to another country for manufacturing, another country for packaging. Maybe here we have the capability to use these chips, make the boards. Okay. So what I want to give an idea is, this is one side is the manufacturing. At a high level, you can say that that's the front-end manufacturing and back-end manufacturing. The front-end manufacturing is going to be your silicon, making the silicon, everything. The back-end could be the packaging. These are different abstract levels we have it. So what is, let me just tell about the kind of design procedure which we follow here. So you need to start with the requirement and specification. You're having a, you want to make a, uh, let's say, a processor, a small microprocessor. Then you need to come out with the spec for it, right? What should be the number of bits, address bits, or data processing? It should be 16-bit or 8-bit. Should it be multiplex, non-multiplex? What kind of decoding you want? What kind of interfaces it should have? What should be the number of cores you want to have? There are a lot of things which need to be decided, correct? That's a requirement or a spec. This could come from the customer, or you are just doing it for your own R&D chip, right? Then you separate all the small parts. Okay, I need to design the core. I need to design the UART. You need to design this SERDES, some deserializer or a serializer, something like that. So you take each part and see what can be, really needs to go into hardware and what can be coded in software. And what can be put in memories or LUTs, lookup tables, and other things you would have found out, right? So these decisions have to be taken. Why do you want to have a hardware? Because hardware gives much faster computing than that software, because software is finally converted into execution in hardware, right? So it takes so many more cycles, but when you have it directly in hardware, it is going to be much faster, right? That's the reason why you have co-processors in camera systems and optical systems, or you have the math processor, right? You have a separate processor for math. You don't use a general purpose processor for not for calculating these things, because it's going to be more inefficient. Whereas here you are customizing and making the hardware for it, correct? So you have to make a decision like, okay, this is the speed at which the hardware is working, and this is what the data rate which is going to come from my camera or something. Then I need to process only in these things. So this processing engine can be in software. Maybe I put the code in a ROM and keep it, and maybe it can, while booting it, it can execute that code, and that's enough. So the decisions have to be taken, what needs to be coded in software, memories, and what needs to go as a hardware or as a chip. Then you come out with something like, you try to do in between some system Verilog code to see whether that's correct, or even C can be used. C++ are also being used to simulate whether that's going to work well or not. Because you have a lot of interacting systems, right? Then when you have your specific thing which needs to be implemented in hardware or in a silicon, you go for something called RTL description, or the even higher level is called the behavioral description. Behavioral description is just like in your computer code. You tell that, okay, if this is the case, okay, you have to do this, otherwise this, all those kind of things can be done. RTL is one step lower to hardware, because you are trying to tell in terms of data transfer from register to register. Why you have registers? These are pipelining registers, right? They try to give you, maybe there is an initial latency. After that, the throughput rate is higher. You would have learned about it, I suppose. Correct? I'm not going into much detail on the way it is. So we try to describe whatever the functionality or the state machine which is there in terms of RTL or the register transfer logic. And of course, there is a verification which is needed to see whether what you are writing is fine or not. Because one important thing in this process is, as you go and capture a problem at a later stage, it is the cost exponentially grows. If you find an issue inside, or for example, there is a small chip which needs to go into a banking system. And if it is malfunctioning, you see the amount of impact it can have, or it's going in an airplane or a defense or in an automotive thing. You cannot afford to have an error or a issue or something which can happen. Of course, we try to have redundancies, we try to have backups and so on. But still, what I'm telling is that it becomes very expensive when something fails in the field or in the product. But it is much easier to rectify it when it is at the stage of design. Even within the stage of design, you're at the end of it, then it's difficult. You have spent a lot of money on that, and there is a cycle which is involved. And time to market is the key for an industry to be in profit. This industry, time to market is very important. There is a huge amount of competition. Okay, and there are also companies which do reverse engineering, try to take the technology, steal the technology also, right? After you have your RTL description, now you try to convert it into gates. Gates are nothing but you would have heard about gates, of course. I'm sure that you know about the different gates like XOR gates, AND gate, OR gate, which do a particular functionality. You try to put your complete logic in terms of these gates. These gates are having transistors which work in a particular fashion. For example, an AND gate, when both the inputs are high, only then the output should be high. In all other cases, anybody has a question? Sorry, I'm hearing. Is anybody having a question? Okay, maybe I heard something. I'm sorry. Even if you're having a question, I'm not able to hear it. Actually, I'm only hearing bits and pieces. Unfortunately, we are not able to have this as an interactive session because I'm hearing a lot of noises. It's not really your noise. It could be my own echo. It could be some other things which is happening. There is a lot of interference happening. I'm sure of that. So if somebody is having a question or anything, probably somebody has to type in the chat window. I would request if anybody has a question, please raise your hand. Just tell your professors and probably they can help you in writing that question in a chat window and I can try to address that.
Okay,
Assuming no.
We will ask a couple of questions from students regarding semiconductor opportunities so that it may help.
I'm okay to take any number of questions, but the only thing is that I'm not able to understand the question. I'm not able to hear it well. So if it could be put into the chat window, it would be very easy for me. Let me go ahead, but I can take questions probably after we finish it. It's okay.
Yeah, we are hearing, but students want to ask you some job-related and internship questions in the semiconductor.
Okay. Please use the microphone. Yes, sir. You're audible, sir, but there is a lot of echo. Okay, please go ahead.
So my question, how do we do AFLS career option and what suggestions would you give to your students like us who are with an AFLS?
Okay, so I got some part of your question. Let me repeat it. You were asking what are the different career options in semiconductors? Is that correct?
Yes.
And how you should prepare for it? Am I correct?
AFL and semiconductors are
You're interested in AI or semiconductor? Sorry, I'm not able to capture it.
Sir, I actually wanted to ask you about AI, since you have taken a lot on AI. So what are the career options and how to be excel in AI?
Actually, their question is the career option is either AI or semiconductor, which is going to
Okay. So career options in semiconductors and AI, which is going to be more lucrative in future? Okay. Okay, let me answer it. Maybe I'm not, maybe I did not understand the question completely, but I'll try to answer whatever I can. So, in my opinion, AI is an emerging field and it's going to be applied everywhere. But AI is not really going to be a, a separate topic, right? AI is going to be applied in each and every field. Semiconductors is for example, VLSI. VLSI is a field where you deal with the semiconductors, the semiconductor manufacturing, the design process, the verification process. There is something called design for testability, DFT, and there are so many other things which are involved. The analog design is a different one, the digital design is a different one, and so on. Everything has its own scope. For example, AI is going to be applied even in this industry. You even take a mechanical industry, AI is going to be applied there. You take computers, AI is going to, it's already there, and it's going to be more and more of it. So one thing is that whether you want to be working on a hardcore area and then apply AI on that, or you want to work on AI technologies itself. So I would always prefer that you should work on your own thing. For example, you're learning about communications or something like that. That's your interest. See how you can apply AI on your communication topic or whatever it is. I would always feel that that gives you a much better scope, and that will help you to do a much deeper and research, or tomorrow you want to do a deeper work on it, you will be able to do on it. Don't be, I would certainly not really recommend you should be a programmer. You should not be uh, kind of, I want our guys to get into more in technical depth where you can go into a topic where you can do research on it and develop on it rather than doing something, where you really don't need an engineer. When you say engineer, you should be able to do research, develop more things based on the science, what you have learned on it, right? So I'm not sure, but if you're asking about career opportunities are everywhere. You will get into anything, I'm sure each one of you, after 5 years or 6 years, you'll be settled in some company or other doing some work. But I would always say that look at the things which is interesting to you, focus on that. Don't go by the industry trend. Okay, you have already chosen something. You're already in a good university with computer science or EC, or I think you're already on it. Just see which is going to be, because this is very broad again, right? VLSA is one part, communication systems is another part of it. You may have microwave, you have so many other things, or electromagnetics and so on. See what is more interesting to you. And AI and other things, you can think about how to apply to make it better. Or if you're a computer science student and you want to work on completely on AI, that's a different thing. Which means that you're more interested in generating different models and giving it to it. But even a person, suppose you're working on a hardcore a communication systems thing, you know how to make the best model because you know the system well. So based on that, you develop it. It's beautiful. It's going to be the most optimal. But if somebody else who does not know much about it, he tries to do it, it's not really all that great. So it's just like, right? See, most of us, I want to also, we go to US and everything. They don't really work on the core of it or the main. And let us also be very open. Even you may be in a multinational company in Chennai or in Bangalore, Hyderabad, wherever you are. Are you really working on a very core area, niche area? Probably the best is being taken and being kept with some people, and probably that's in US or in some European country, wherever it could be. We may be doing some work which may not be that significant, which means that what I'm finally coming to say is that see what interests you, be have the technical depth in whatever you are learning, whatever is your interest. Keep that, develop over that. That will give you, then you have opportunities everywhere. Once you have your fundamentals, your technical depth is good, then I think C is the limit. You will be on in demand. Like in one commercial I saw, the interview is taken by the company guys. Right now, the student, they are so much in demand that they come and sit. Many companies, they come and sit for a single student. It could happen. Why not? If you're a good student, if you're technically very good in what you are. So, in simple and let me. I think I've been repeating the same thing again and again, but focus on the thing which interests you, whatever you are learning. I think that should be enough. And AI and other things you can apply on the top of it. And
Yes,
don't go
sir.
by at one time I know that biotechnology. They said biotechnology trending. Everybody goes to biotechnology. At one point of time, there is another field, information technology. Information technology, everybody goes. But I'm not telling that's bad or good or anything. Go by your interest rather than being driven by the current market trend or industry thing. And this is an evolving field. Everything is going to go on. I'm not sure whether I answered your question.
Yes, sir, I got my answer. And my other question would be, since we are electronic students, we are much more interested in semiconductor part as well. So are there any career opportunities and internship opportunities you provide from your and European students like that?
Can you again repeat your question a little bit slowly because there is a lot of overlap.
They are asking about internship opportunities in your country.
Okay. Internship opportunities, right? Yes, there are internship opportunities. Uh, Different companies they provide at different times. Okay, and let me be just very open. I'm not going to please you guys are they many of these companies, that big companies, let me put it that way, they have tie-ups with many of the universities. So usually when they feel that the market is good, they go get a bunch of people for internship, and many of these interns they are converted into regulars. So there are internship opportunities, and most of the internship opportunities are done during the campus placement itself. Okay. Otherwise, you have to go and hunt, look for internship opportunities. But if you have LinkedIn profile and everything, subscribe to those companies you are interested or doing internship with. I'm sure they advertise that telling that we have internship opportunities, you can apply for it. Or if you have somebody working in the company, try to go with the reference. That's a little easier.
And yeah, sir, what skills are required to excel in the industry?
What skills are required to excel in an industry?
Sorry?
Semiconductor industry.
What skills are required to excel in semiconductor industry?
Skills are okay. I would say the most of the things which are important is what you are learning in your classes, right? Are you good in that? Have you, because when if I'm to take my if I need to take some people here, or if I need to take some people for internship, I'm going to give them training. I'm going to give the necessary things to them to develop the skill sets what is needed for that particular job or that particular thing. But what is more needed is your fundamentals. We test your fundamentals. That's the most important thing. So your superficial knowledge doesn't help if your knowledge is superficial. So that is the reason why I'm telling when you are learning, learn it with interest, try to go in depth and understand what it is. You have lot of sources now, right? You have YouTube videos and other things. So use that and try to see whatever subjects you are learning. If you think you are good in a particular, for example, place and route or design for testability or analog this thing, just try to see where you are good at and try to go for internship or opportunity in that. Analog, some people could be good in analog VLSI, right? Then go try to look for opportunities in analog VLSI. And I'm sure that even if there is a person who is coming from a tier one very good university, but there's another person who's good. We find a lot of good students from tier two or tier three universities also. They're just, the only thing is that they may not get the right opportunity. But the difference is that you just need to be good in fundamentals, understand well, and I think that's it. For that, I don't think you need to go and try to learn some computer programming courses, two, three things. It adds value, but
Okay, we will take one more question from and we will.
yeah, sure.
What are the fundamentals of basics in semiconductors?
What are the
Fundamentals we need to learn to excel in
Fundamentals to fundamentals to be learned to excel in semiconductors.
fundamentals? The
Then
fundamentals are very
fundamentals.
simple. See, I'm sure your curriculum is so good. Okay, if you learn your things well, okay, learn your things well, whatever you have in it, interact with your professors, go in depth, go to the lab, experiment those things. Okay, marks, I'm sure marks and other things are important, but go interact, uh, try to work on whatever you are learning. That's more, that's the fundamentals, right? That is good enough. You don't have to do anything extra. Whatever you are learning, do it well. That's good enough. That's my feeling. That is what I feel.
Okay, any other? Okay, then thank you for your time. Share with our students.
Yeah, you're all most welcome. I wish you, I think the students, I wish you all the very best. Don't be worried about your careers. I'm sure all of you will settle well. You're in a good place. I'm sure whatever your professors are guiding you and just try to follow that. I'm sure that's going to do a lot of good things. Thanks, sir, and thanks to all the professors for the opportunity. Wish you all a great day ahead. And in case you have any questions, please, through your professors, you can get in touch with me. Okay, I'll try to answer as much as possible.
Okay, sir. So I will collect, I will gather all the questions and like mail and
Sure, sir.
am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Okay, okay, thank you.
Thank you very much. Thanks, all of you. Have a good day.
Okay, this webinar is paper talk. So this is the actually you have to learn something from this expert that is Mr. Ravi, and he is my those who are sitting in there with bracket in grade during 1997 to 2000. He is my classmate and a close friend. So he is working in Bangalore and all our networks are working in all semiconductor industries in and around the world. So we can connect you with the different people with different aspects. That is what we are trying. So this is one of the members. He cannot, if you go to Bangalore, you cannot go into this family. He is the CEO of the company. Okay, so you have to learn only one thing from him. Even though he is the CEO, you can see he is getting credit. That is the identity of the person. So there is no prosperity in the Bangalore that you can afford any. You have to follow the code and this company is next to India. It is that is the analog devices. One of the topmost semiconductors company functioning in headquarters in Delhi. And what you will be the system design engineers. The company is a package of 50 lakhs per annum or 70 lakhs per annum of electronic package. And once you complete your intern, after that you will be in a regular position. You will be placed in engineering development. So our aim is to connect with this person. I am trying to connect one of our students with him, but that is a very big challenge. Since he is not ready. We are requesting only one student, but their expectations are I cannot be able to explain. They require 50% from student level, 50% from university level. So they don't teach from using this presentation now. We don't tell anything from scratch. Once you get to work, you have to see the results. With the results, if you go to review, you will yet we said if you want to learn it, then it's not possible in this. So that's why we are telling you to make use of the resource, learn something here, upgrade your skills, and go to industry, then only you will get a job. So this is why NMC coming to college, sitting here, and going away with the lack of certificate, no one will get a job anywhere. This is what I am telling. Go and work with your faculty, write papers, research articles, go and publish articles, write the papers, publish the degree profile. Your degree profile is the main. If you showcase degree profile, connecting with this person is very easy because I don't need to explain about you. I can just share your degree profile. That is more than sufficient. That's why we are coming you. But no one is saying that no much about you are ready. That's why you are very valuable. Then what is the need of creating degree? One student is fixing one cartoon image. Then how can it introduce you to the person?
Our actually main intention is to improve the knowledge of that kind of person. I think all of you know about device company. How many of you know about device company?
You can go anywhere like industrial visit to Putnam.com. Later you can go. You cannot go to this company. Even maybe you say I am not able to get even though he is a close friend, I cannot be able to approach him. I can go. As a friend, I can go. But as a student, as a faculty, along with some 50 students, I don't have a chance to meet him. That is the problem. This fellow, along with him, we studied international system, PhD, everything is by management. Along with him, only we will do experiments. But you can see his position.
And he is our device expert.
He is our device expert. He written servers for you. He has made servers in written by this fellow. So we are trying our development. That's why continuously technically improve your degree profile. Not only that, we are also telling. Yesterday also we made meeting. What we ask the only question is how many of them completed degree? How many of your students completed degree profile?
And one thing I am telling you, we are not we are not different universities. Okay. So our main intention is to target this university. We will top 5 in it. But we have time. So within that period, we have to be a top 5 university area. Top 5 is society. So that definitely will help. But I think the cooperation is supported. If you want not then on universal flights, faculties are not all faculties are being converted. Okay, but the problem from the student side, your support. See, in ECD programming, in ECD, how many students process paper? How many students submit paper? Departments. Just raise your hand. Total how many groups of UCI today? Total how many of them submit paper? How many of them are provided? How many of them are provided? You submitted any paper? Any conference paper? Why are you encouraging to submit conference? Yesterday I already discussed with Mani sir. For getting interesting job, there is a one more